PPV, we have completely finished studying about the informal guidelines for relational schema design. And now we are going to focus on formal guidelines for relational schema design. When we are focusing on formal guidelines, we should learn about functional dependencies, or as we call FDs in database management system environment. Let's dive right in. Functional dependencies or FDs. Functional dependencies are just some rules. Okay. Some people call them as constraints, but FDs, hereafter I will not call the word, use the word mostly functional dependency. I'll be using the word FD mostly. So functional dependencies are constraints. They are constraints or rules. They are constraints that connect two set of attributes in a specific relation. Okay. In a specific, this one we are speaking inside a relation, not between relations like R1 and R2. We are talking inside one relation. Okay, we know in a relation there can be multiple attributes: A1, A2, A3, A4, A5 until AN. Let's say there is n number of attributes in relation 1. Well, if we can gather this around as a set, if we can put them into a set or multiple sets, well, then we can actually create some sets of attributes. And FDs are constraints that create connection or that create relationship between these attributes. It can create relationship between these attributes. So FDs are constraints or rules between two sets of attributes in a relation. So what does this constraint do? FD do? It establishes relationship. It establishes relationship. This is how you can simply understand FDs. If you can't remember all these things, just keep in your mind FD is something that creates connection in between attributes. We normally say a relationship creates interaction or relationship between two entities. That's what we normally say. Now we are going deeper. We are diving in deeper. We are speaking for a single entity, or in this case, for a single relation. Inside this relation, we have multiple attributes and we can put them in sets. And FD creates relationship between these sets of attributes. That's what we are going to learn. Okay. Actually, this FD generalizes the concept of key. You must have learnt about key attribute when you were learning about entity relation. I will be covering entity relation in a future playlist. Don't worry. But for now, just keep in mind in entity relationship we study about different types of attributes: single valued attributes, atomic valued attributes, multi-valued attributes, composite attributes. Similarly, we are going to learn so many attributes. In those, key attribute is a very important idea. Key attribute is a very important attribute, as this attribute is used to identify any tuple in that relation uniquely. What is a key attribute? Key attribute is an attribute that is used to identify tuples in a relation uniquely. And those who are working in MySQL environment, or any other environment related to DBMS, you normally know this key is also known as primary key. This key is also known as primary key. And FD actually generalizes. You can actually pick a primary key by using your logic. Okay, your common sense is enough to choose the primary key. But now, by using FD, we are generalizing it. Generalizes the idea or the concept of key. Step by step, we are going to learn how to choose primary key of a relation. And this involves decomposition also, sometimes union, sometimes even augmentations. That depends. But because there are multiple types of DBMS, there are multiple types of relations. So we have to keep in mind we need something that actually makes this process mechanical rather than based on our common sense. Let's learn about FD's notation. Now, notation. When you are considering about FDs, when you are considering about FDs, please visualize whatever you have learned in relations in mathematics. Functions, you must have learned about functions in mathematics. For example, f of x is equals to a x to the power n plus a x to the power n minus 1. Okay, a0, a1 plus a 2x to the power n minus 2 until a n x to the power 0. This is what we call a polynomial, or this can be a function. This can be a function depending on some conditions. Okay, but keep in mind, whenever you are speaking about relations, please visualize whatever you learned in functions. Whatever you learned in function, keep that in mind. Always keep that in mind because it is going to be used. It is going to be useful. So keep that in mind. So the notation is x functionally determines y. X functionally determines y. This is what we call the notation for functional dependencies. This is what we call the notation for functional dependencies. Well, you may ask a crucial question: what does x? What is x? What is y? Well, I will be explaining that in a moment. First of all, you just understand what this notation means. X arrow y. This means x functionally x functionally determines y. X functionally determines y, which means you can consider of x, capital X in this case, as the independent variable. You can consider like that if you are more mathematically oriented, as the independent variable. And y is functionally dependent, on x. This we can call as the independent variable. Sorry, dependent variable, y. Y is the dependent variable and x is the independent variable. You can consider like that. Now, I will go through the notation with proper definitions and all. So the proper definition, we'll look into it. X functionally determines y. Well, first of all, we need a relation. So let's name the relation R. And let's say X and Y are non-empty sets. Non-empty sets of attributes in R. Do you understand? R is a relation. We know how relation looks. It consists of multiple attributes, one or more attributes, and X and Y are non-empty sets of attributes. These three attributes can be X and these two attributes can be Y. Or these three attributes can be X and these three attributes can be Y. It depends. It depends based on the selection of attributes. But keep in mind, X at least should have one attribute, Y at least should have one attribute. That's why we use the word non-empty sets. This is the second this is the second condition for this specific FD. All right. Now, this is the actual definition, how we can define this in terms of words. In terms of words. In a relation R, where X and Y are non-empty sets of attributes in R, where X and Y are non-empty sets of attributes in R, the relational instance R, the relational instance simpler, the relational instance simple R, okay, I can't say simple, okay, simple R or lowercase r of relation R. Okay, now we have a relation, we have two non-empty sets of attributes. In that relation, if you pick a random relational instance R, any relational instance, any relational, let's say any relational instance R of capital R follows or obeys or satisfies, whatever the word you like, obeys X functionally determines Y if and only if any tuples of R T1 and T2 satisfy the following rule. Satisfies the following condition, let's say. Following condition. You can say holes also. If you prefer different words, you can use holes here. In a relation R, we have a relation, and in that relation, we have X and Y sets of attributes. Let's say these three attributes are X set of attributes. Well, that's not simple X, capital X. And let's say there is some attribute that's called Y. Okay, let's also uppercase Y. And if you pick a random relational instance with set of tuples, okay, you're picking a relational instance R from this relation R, and this R has the tuples T1 and T2. They should follow the following condition. Okay, if T1 dot x is equals to T2 dot x, T1 dot x na inna meaning? Well, in the T1 tuple, there must be a value for x attribute. The x set of attributes, right? X set of attributes. Let's say this is T1, and let's say this is T2. Let's say this is T2. If the value for a T1 for x attribute 1, for x attributes are 1, 2, 3 respectively, and T2 has the same values for x attributes respectively, 1, 2, and 3, well, then T1 dot y must be equals to T2 dot y. T1 dot y must be equals to T2 dot y. Well, let's say here we have the value a, simple a or lowercase a. Well, here also the value must be a. This is the definition of this notation. X functionally determines y. X functionally determines y. This one may look like a waste of time for you, but if you understand this, if you understand this clearly, anything that comes after this will be like a piece of cake for you. Any FTs, there are different types of FTs that we are going to, different types of axioms that we are going to use to find out the FTs, but it doesn't matter. Why? Because you understand this. Now you know what you are looking for. Now you know what you are looking for. So this will be easy. To make this a little bit clearer, I will give you another example. Maybe a big example. John clearly. Let's say there is a relation R1, okay? And we have three attributes, only three attributes, X, Y, and Z. There are values for X, 1, 2, 3, 1, 1, 2, 3, 2. And there are Z values. Any value you can put A, B, C, D, E, F, G, H. And for Y, if R1 satisfies X functionally determines Y, the value corresponding to all ones for the attribute Y must be the same value. So if you put capital A here, uppercase A here, here also the value must be uppercase A, here also the value must be uppercase A. For 2, if you use the letter uppercase B, well, here also the value must be uppercase B, here also the value must be uppercase B. For 3, it must be, let's say it's uppercase C, well, here also the value must be uppercase C. If this happens only, X functionally determines Y. What if, let's ask question. Instead of C, if we had uppercase D, what happens now? Well, here the values do not match. Here the values do not match. For 3, there are 2 different values. Therefore, we can say this is not an FD that is followed in relation R1. It is not an FD that is followed in the relation R1. This is what we call functional dependency or FD. I hope you understood what FD is. In the next video, we will be looking at full functional dependencies and partial functional dependencies.
Thank you for exploring functional dependencies with us. If you enjoyed this video, give it a like and share it with your friends. Subscribe to the channel and hit the notification bell to stay updated with upcoming lessons in the normalization series. I'll meet you in the next video. Until then, keep learning and stay curious. Bye bye.